Okay. Hello, everyone. Welcome to week 2 of SUMO's speaker series. This week we have Kyle Mclean from Blueprint Labs, and he's going to tell us a bit about what he does and a bit about the company. Remember to stay into the end to make sure you can fill out your PEP form to get the PEP package for this speaker series. And yeah, I'll let Kyle, he's going to tell you about himself, what he does, how Blueprint Labs work, and I'll let him take it away. Thanks, Kyle.
Thanks for that. Yeah, so my name is Kyle Mclean. I'm a control systems engineer at Blueprint Lab. We're a robotic company located here in Sydney who develop robotic manipulator systems for harsh environments. As you'll see from the video on the screen, most of our manipulators end up integrated on underwater vehicles. This is because the subsea market has traditionally been our main target sector, with applications in ocean science, offshore energy, naval, and even emergency services. Recently, we've also begun targeting other sectors that require robustness, including land forces, nuclear, and space. Basically, we develop systems to remove humans from these dangerous environments. This has been achieved through 2 lines of subsea manipulators, Reach Alpha, which is a small inspection class manipulator, and Reach Bravo, a larger light intervention class manipulator. In 2017, Blueprint Lab released our first grabber for underwater environments. This was a dual function manipulator, which was the smallest in its class at the time. In 2018, the 5-function Alpha line was released, which aimed to provide greater dexterity through more degrees of freedom. And to aid controlling all 5 joints simultaneously, the master arm was a natural development in the following year. After the success of the Alpha line and requests from many stakeholders, the larger and stronger Bravo line was released in 2020. The system also extended on the Reach Alpha to include extra degrees of freedom and more advanced control methods. As the Bravo system has become more mature, we have extended towards development of vision and automation systems. These systems are still under development. However, we've made some pretty good progress in recent months. To interface with the manipulators and provide feedback to the users, we also develop our own topside software and one-to-one controller. The master arm is a traditional style controller for subsea inspection and intervention tasks, and it allows the user to intuitively control the manipulator with relatively low threshold for entry. Reach Control is our in-house topside software, and it allows the users to control, configure, and communicate with the manipulators. Reach Control also enables users to view the current state of the manipulator, which could be operating at 450 meters underwater. And it achieves this through feedback of the manipulator's position, velocity, current, torque outputs, along with the climate and error state of the arm. So there's actually a lot of effort that goes into making these manipulators. Even to spin the motors requires many layers of electrical, mechanical, and software design. Here are just some of the components that I've worked on in my time at Blueprint Lab. From the communications between the topside software and the manipulator to fault detection on the joints themselves. Each of these components is critical to the function of the system. And if any one component is not up to scratch, then it could have a detrimental impact on the system's performance. And in the worst case, it could even cause damage to expensive infrastructure or even cause harm. Because of this, verification is probably one of the most important and time-consuming points on this slide, although it requires a lot of details to go into, so I won't labor you with the details on that. I am going to dive into a few other topics though. So I think joint control is probably one of the first topics that any mechatronics engineer would look into when deciding to develop a manipulator. Proportional interval controllers form the basis for much of our motor control architecture. We use a cascaded structure where each loop generates the set point for the subsequent loop. Here, we can see that the position demand, we can see that from a position demand, a velocity demand can be generated. Then a current set point is produced, and then a voltage. This voltage demand is mapped to the 3 phases of a brushless DC motor by the field-oriented control algorithm. These signals are then sent to the motor, which drives towards the generated set points. As I mentioned in the previous slide, to control brushless DC motors, we need to generate 3 voltage signals. The best way to achieve this is through field-oriented control. This technique uses the Clark and Park transforms to simplify the control problem quite significantly. And it abuses Kirchhoff's current law. By abusing Kirchhoff's current law, the Clark transformation can be used to project the 3 AC signals onto 2 stationary axes. You can see on the slide that we have the 3 AC signals there, and they are getting transformed into the 2 signals by the Clark transformation. And then following that, these 2 AC signals are transformed into 2 DC signals, quadrature current and direct current, via the Park transformation. With this simplified problem, it is now possible to use a basic PI controller to produce the voltage set point. The voltage is then passed through the inverse Clark and inverse Park transformations, and the 3 voltage signals are restored. Since the quadrature current is directly related to the torque output of the motor, we can set this value via the velocity controller output. That was seen on the previous slide. The direct current is then controlled to a value of 0 in regular circumstances. However, there are some cases where you might want to modify this value to produce additional velocity through a concept known as field weakening. Additionally, we can augment this algorithm with space vector modulation. This is an example of a signal after space vector modulation has been applied. In this case, we can utilize close to the full voltage capacity of the system. Now that we have a way for controlling the joints, we must consider how to calibrate the gains of these controllers. To achieve this, we use the motor model along with the controller and sensor sample frequencies to inform how the gains are computed. We then define the controller's bandwidth to determine how aggressive the controller will respond to a set point. Another important concept for manipulator control is kinematics. In this setting, kinematics defines the relationship between individual joints and the global frame. For example, if each joint angle of the manipulator is known and the relationship between each link is well defined, then it is possible to determine where the end effector is with respect to some reference frame. It is also possible to do the inverse of this problem, where we determine a set of valid joint angles given some desired end effector position. However, one issue commonly encountered when attempting inverse kinematics is the event that multiple solutions are valid, or that no solutions exist at all. To overcome this issue, optimization-based methods are typically employed to find a solution that is close to the desired set point. Now that we understand how to move the manipulator's end effector, we might also want to add a degree of autonomy to the process. In the Bravo system, position presets are implemented to provide the user with stow and deploy positions. Objects are also defined in space to provide key cut zones for the workspace. When a user decides to use a preset position, the system will plan a path between its current and desired position. So as you can see, there's a lot of moving parts that go into a system like this. I've just shown a small subset of the topics that I've worked on, but really there's a lot more that aren't even shown on the slide. Does anyone have any questions regarding the Bravo system, how the Bravo system works at all? Just open up for anyone that has any questions there.
Guys, feel free to just unmute yourself and shout out any questions you may have.
I'm also looking at the chat here if anyone has any questions there. Otherwise, I'll move on. So I've got a question from Will. He says, do you find mechatronics engineers working across multiple different systems of the manipulators, or are they more likely to specialize in either software, electrical, or mechanical? So it's a little bit of both, actually. For me personally, I was employed as a software engineer, but I spend a lot of my time working on hardware, doing fault finding for electrical stuff. I do a lot of the control backend for the joints. I also do some of the control backend for the base computer, which provides kinematics, inverse kinematics, and some of those more high-level functions. I haven't done any mechanical sort of stuff yet, but if you're an engineer that has a mechanical background, there's no reason why you couldn't do software and mechanical as opposed to software and electrical. I think that might be it for the questions there. Yeah, so following on from that, stakeholders are probably one of the most important parts of our business. In fact, we wouldn't have a business without them. And for this reason, it's really important that we listen to them. So here's some of the input we recently received from one of our stakeholders. They were after a solution that would aid them to easily turn an industry standard ball valve. The issue that they were facing when trying to do this task manually was that it was very difficult to draw an arc through a space using a traditional controller. Thankfully, it's actually quite easy to use software to remove this complexity. So this is one of the solutions that we came up with. The solution would allow the user to define a fixed point that the end effector would rotate around in space. And then they could simply just supply a velocity demand to rotate about this point and operate the valve. We named this arbitrary point the work frame and developed a mode to operate around this point. In this mode, the users, as I said, supply velocity demand that is translated from the work frame to the end effector frame. This was achieved by considering the common point between the two frames, the base frame. Homogeneous transformation matrices were constructed to define a relationship between the frame, between each frame and the base. From these transformations, a new homogeneous transformation matrix was constructed to map between the work frame and the end frame. Now the angular velocities about the work frame could be mapped to translational and rotational velocities in the end effector frame. Finally, the standard end effector inverse kinematics could then be used to compute the joint angles required to satisfy this demand. As part of this solution, we also developed some new components for the graphical user interface. These components were developed to communicate to the user via feedback, send control demands to the manipulator, and update the pose of the work frame. For each of these components, we were required to create 3D animated widgets to display feedback and allow the user to modify variables. This process also included utilizing knowledge of the manipulator's kinematics, along with similar transformations to the previous slide. This solution also lends itself pretty well to future automation. Consider that an equal tag is located at a fixed point with respect to the valve handle. This tag could then be used to supply the system with the valve's location. The valve could then be autonomously operated, making the task even more easy to perform. This is possible since the pose of a camera with respect to the tag can be interpreted as a perspective endpoint problem. Using a calibrated camera, a set of n 3D points in the world can be mapped to a 2D projection in the image. A transformation between the camera frame and the manipulator base can then be used to determine the target's location. Here's an example of tag tracking using this method. This kind of tracking can be easily adapted to many industry problems and is a relatively reliable method for automation. Does anyone have any more questions on the stuff that I'm talking about here?
I have a quick question. How would you reliably turn the 2D camera array into an actual 3D position in space? Would you have the tag as a known size? Would you know the size of the tag? Or
yeah, so two things you need there is a tag with known points, and you also need to have a camera that is calibrated.
Yeah, right. Okay.
So with those two things, then you can back calculate the distances quite reliably.
I saw in one of the videos before you had a manipulator with 2 cameras on it. Do you think you could synthesize the information for 2 cameras for a more robust solution to get the distance?
Yeah, I don't believe we've done this yet, but it's definitely something you could do. And it also supplies the system with more robustness to occultations. So, for example, that paddle has to be held to the side of the Bravo, like to the right side of the Bravo on the screen, because if it's on the other side, occultations stop it from being able to see the paddle. Yeah. And that's also why there's 2 tags in that picture. So that was to provide extra redundancy there.
That's interesting. Thanks.
So yeah, a bit about where we're at right now. So in recent months, our team has grown quite substantially, and we've hired several R&D engineers and a load of production technicians. And we also have plenty of support staff, including tech support, sales, and marketing, all coming into the group. Just got another question, I think. I'll just answer that one before I continue. So I'm interested in knowing more about your background. How did you find yourself working at the company, and what does the task do? What tasks do you typically complete on a normal day during work? All right, I'll come back to this one after the next 2 slides. Yeah, so we've currently got our team going quite a bit now. And yeah, actually, that's all I have to say with that slide as well. Yeah, so about me, I'll just look at that question again so I answer it properly. So I guess my background is a bit along the lines of what I was talking about in these in the earlier slides. So I started at Blueprint Lab, I think 2 years ago now. I came from the University of Newcastle, where I did my thesis on a particular type of control theory. When I started at Blueprint Lab, I started writing a lot of the low-level drivers for the embedded systems, and also started picking up some of the control stuff. And that's pretty much what I do for my day-to-day most of the time. Apart from that, I do a lot of like system verification, acceptance testing, and other sort of systems engineers roles as well. The way that I found myself working at the company was actually through a connection to a PhD student at the university I went to. So nothing special there. Yeah, is there any other questions? I think yeah, that's it at the moment. Does anyone want to know about, I guess, the kinds of jobs that we hire for, or anything else along those lines? Another one from Will there was, is there anything that you didn't learn at uni that you wish you had before you started at Blueprint? Actually, I think I was quite fortunate in the stuff that I chose to do for my thesis. I ended up learning a hell of a lot of things that were actually very relevant to sort of my work at Blueprint Lab. I learned a lot of things that aren't directly applicable, but also just provide me with a lot of the foundational knowledge that I use today. So I did a lot of my thesis on dynamic control systems. And although we don't really use dynamics in our robotics, having that background knowledge and sort of the ideas and concepts that they use towards like stability of controllers and things like that was very useful when I started at Blueprint. One from Amelia is, were you always set on doing engineering or mechatronics? Was there some sort of discovery process that you went through before deciding you wanted to work at Blueprint Lab? Yeah, I was always really interested in mechatronics. I think I decided that I wanted to pursue that career in about 10. And at the same time, that's when I started fiddling around with things like homemade quadcopters and stuff like that. Realizing that they didn't work very well. So writing my own PID controllers to stabilize the thing and stuff like that. Will Thorpe also asked, okay, what did you do for your thesis? So my thesis was on a particular control formulation called Port Hamiltonian control, sorry. And it essentially uses the Hamiltonian model of a mechanical system to inform how to control, how to build a controller for that system. It also provides quite a bit of insight as to how to define like the controllers themselves, I guess. What is the R&D process you go through at Blueprint Lab in terms of software, hardware, prototyping, testing, etc.? That's quite a loaded question. The R&D design process, it, I guess, sort of begins with an idea from typically Paul or maybe some custom input. So Paul is the CEO at Blueprint Lab, or some custom input that comes in, and then that's sort of interpreted as some system requirements. From that point, it goes through some basic sort of checkpoints where we work out if the solution, if we can actually find a solution to that, and sort of feasibility studies. Following that, we would prototype sort of a solution in-house. So just kind of the quick and dirty hacks to get something working and seeing if we're right about the feasibility of it. And following that, it starts to follow a bit more of a rigorous sort of process to develop that solution. I could probably do another whole presentation on that R&D process, but I can't speak about it too much off the top of my head. I think But Evan, the person that just wrote what is the R&D process, said basically, where does the R&D process start? So yeah, that's what the founders usually, they come up with the good ideas. That's not to say that we don't have any influence as well. I feel like there's a lot of ideas that have been propagated into the system from even people starting as interns and other things like that. Everyone's really open to good ideas at Blueprint. Is there any other questions? What kind of roles do interns carry out? So usually for interns, we try to find sort of an isolated project from the rest of the system that they can pick up themselves and really just drive the project, which I think is really good for someone that's just come out of uni to sort of experience like holding on to one of these projects and really shaping how it goes. And it's good for us so we can see how that intern can work on their own, like autonomously. They will also carry out some other tasks that we might need to do that are related to systems that already exist as well. Another one from Robert is, what other industries does Blueprint Lab get involved in? So the industries that we're involved in were pretty much highlighted in that probably second slide. Let's see if I can get that one up. I'll try and think of anything else that we. Oh, sorry, I just said them. I didn't. But yeah, so we are part of a lot of ocean science, offshore energy, naval, emergency services, land forces, nuclear, and we're trying to get into the space industry as well. In terms of like, I guess an interesting one is emergency services. So in Canada, one of our main clients, they use the alpha grabber to recover victims that get trapped under the ice in Canada. So unfortunately, people might drive their car into the water, they get stuck under the ice and no one can retrieve them because the water is so cold. So they'll send a grabber in to retrieve the body, which is kind of good for the victim's family, I guess, in that circumstance, because they get a bit of closure by having the body.
Kyle, I got one more question. What do you see for the future of Blueprint Labs in the next 5 or 10 years? Do you think do you think the plan is to try stay up to date with like groundbreaking new engineering software and hardware, or broaden the horizon of the company and try and make different types of products?
I think I know one sort of direction that we're taking is moving away from solely underwater. So we're trying to target land forces and sort of other harsh environments other than subsea. In terms of other products, I don't see us like having other product lines other than, I guess, just robotics in general. So probably along the lines of manipulators, but also more focused on the autonomy and the sort of like the vision systems and stuff that I was talking about there, and very tight vehicle integration, I think, is going to be important. So sort of having an entire solution rather than just like, here's a manipulator, like work it out yourself. Actually having a very well integrated system is important. Think about like the iPhone sort of ecosystem. We want to have that for a manipulator, like out of the box, sort of just works kind of feel.
Yeah, that's awesome. Cool. I think there's one more question from Rohan in chat.
What are we planning to do in the space industry? I actually don't know like very many details behind this, but I know that we've signed a memorandum of understanding with, I'm not sure which university, and that's part of the defense, I think, Moon to Mars program. So in terms of space, yeah, we essentially want to be able to ready our manipulators to be in the harsh environments of space, which poses sort of some different challenges in terms of electromagnetic radiation and things like that as well. Yeah, so we've got quite a few international hires at Blueprint, actually. So we've got some South African people, some a French person, and what else have we got? South American. So there's it's a very multinational company. I feel there's people from everywhere here, and it's really good. It's a fun environment to be in with so many different sort of ideas and opinions and things like that, which I find really cool. So Robert also asked, what's my favorite part about working at Blueprint Lab? I think I'll rephrase it a bit. Maybe one of the most fulfilling parts about working at Blueprint Lab is just having the opportunity to really drive like a product or solution, like shape it to be like something that you've envisioned. I think we're very open to like ideas and yeah, if you've got something to put forward, then it's always on the table, and people are willing to listen, as opposed to other bigger companies where you might have a great idea, but it just gets sort of trampled on by bureaucracy and things like that. So I think that's good. And I hope that's something that continues into the future. So we did have a role for an electrical engineer that was, well, I don't know if that was specifically electrical, but to ready our arms for space. Think that we have found someone for that position, but I'm not 100% sure. And then the other question is, what's the pay like at Blueprint Lab? I can't speak numbers exactly, but yeah, it's definitely competitive. And I guess it's based off your experience. It's probably the answer that I have to give. Oh yeah, that was the next one. Sort of, I guess, industry standard. So would being an international hire affect your ability to work on Department of Defense projects? I actually don't know the answer to that question, unfortunately. I guess it could have some effect, but I don't think it would be like a reason why you wouldn't necessarily get employed at Blueprint Lab, but it might pose restrictions on the kind of work that you can oversee, I guess. I'm not 100% sure though.
You mentioned before that you have quite a lot of manufacturing-based roles at Blueprint. I think it was like the highest number of out of all on that slide.
Yeah.
So what would the qualification for someone under that role be? A full engineering degree or something maybe lighter? And B, how much of the like ground up manufacturing is done in-house? Like where does it kind of begin for you guys manufacturing, or is it mostly just maintenance work that you guys do in-house?
Yeah, okay, so the production technicians don't necessarily have to have a degree. We also have quite a few production engineers, but as we grow, it's more economical to have technicians rather than engineers working on the production line. So I think the production managers, they have engineering qualifications, but most of the other technicians that have been recently hired, at least, don't have qualifications at the moment. They're usually quite skilled in terms of like assembly and electronics and things though, and usually have some like pretty good like background in hobbyist electronics and stuff like that. In terms of where we start for the production process, so we get we do the entire design of the system in-house. We procure parts that are like standard if possible, because that's typically cheaper. But in terms of like, I guess the design for Bravo, we pretty much design all the external parts designed in-house and then like CNC milled, so manufactured overseas. We get the motors from a standard sort of motor manufacturer called TimGap, but they just come as like a stator, which is just a coil of wire and a magnet, and then we fit the rest all together. So we supply all the external sort of mounting around that. We also then purchase from another supplier the gearboxes which go into the motors, and then yeah, all that stuff comes together in our production facility, and we assemble it together with quite a, I guess, complex assembly process, considering the amount of like electronics and mechanical hardware that needs to fit into such a small cavity, but also maintain like the waterproof specification, and a whole bunch of other specifications as well.
Yeah, that's interesting. Thanks. Anyone who's got more questions, feel free to unmute yourself or send them in chat now. And also just a reminder, everyone needs to fill out the Google form I've sent in chat now to secure your PEP hours for the attendance of this talk and our other ones.
So another question is, what kind of monetary constraints do you as an engineer have to work around? So I guess this is more to do with like when we're designing a product, do we consider the monetary constraints of that? And yeah, we definitely do to a degree. With the research and development phase, that's constraint is usually a lot more relaxed, and depending on whether we have funding from the government, it can be even more relaxed in terms of getting a solution together for some like to see if like we can actually get something to work. In terms of production sort of releases of things, we try and get the cost to be like as low as possible, but still meet the requirements, I guess. So pretty much like how any company, I guess, would approach that problem. Yeah. And what advice would you give to engineers starting in the workforce? I guess just like enjoy what you're doing, like really just get into it. If you're like looking for your thesis at the moment now, just try and find something. Don't try and find something that's just going to get you like the box ticked off. Find something that you're actually going to like really enjoy. Spend a bit of time trying to locate that project. Even if it looks like it might be really difficult, I can guarantee it's going to be a lot more rewarding than I guess like some projects where you do something quite simple, but you're sort of guaranteed half decent marks or something like that. And then any advice for someone doing their thesis now? I think the best thing that I did with my thesis is I started writing my final thesis report like 5 months before I was due, and I was finished it 2 weeks before I had to hand it in. And that was probably the best thing that I ever did in my life, because I had no stress at all when I was coming to like having to do my final presentations and things like that. Whereas like people were spending all nighters trying to smash out this report, and they were absolutely killing themselves at the end there.
Okay, I think basically most people have filled out the form now. And if anyone has more questions, feel free to still send them in the chat. But I'm gonna just thank you, Kyle. That was a very interesting speech. I love the graphics in your PowerPoint. it was really interesting company. I've loved learning about Blueprint Labs, and I'm sure everyone will agree with me. And so I'll let everyone go now. If you want to rewatch something from the presentation, this is all going to be recording up on YouTube and with the link to that video on our Facebook. But besides that, yeah, everyone have a good afternoon, and yeah, that's it. Thanks, Kyle, again.
Thanks, guys. Everyone's so polite with all these thank yous.
Yeah, now we'll see the people who've left their Zoom on to try to get the pep hours. Okay, yeah, I think, yeah, you're good to go now. Thanks again, Kyle. That was awesome.
All right, cheers, mate. See ya.
Have a good one. See ya. I'll just end up Zoom.